Alright everyone, since it's already 8 for me, so it's time for us to start. So today's lesson, it's the second lesson of this class, and it's gonna be on triangles. So, you may be asking, well, what is a triangle? The Greek prefix tri, it means for three. So a triangle means a shape with three angles. More specifically, a triangle is a polygon with three sides and three vertices. You might not know what a vertex is. So a vertex, which has plural vertices, is a point where two sides of a polygon meet. So as you can see in the triangle, there are three vertices. And, usually you can see that the vertices are just the points on the very end of the triangle. So here are some arrows that are pointing to the vertices. So triangles are the simplest and most basic polygon because it has the least number of sides possible. If you can try to make a shape that's closed with only two sides, and you'll see that it's impossible because you need at least three sides to make a shape, which is the triangle. And there are some other polygons that we're going to cover later in the course that include quadrilaterals, pentagons, hexagons, or as the number of sides get too large, we just usually just call them by the number of sides they have. So, for example, 100 gon. So, what's so special about triangles? Well, every triangle has certain characteristics that it has to fulfill. So, for the first characteristic is that the sum of the internal angles of a triangle is always 180 degrees. For example, you can see that there's a yellow arrow pointing to the left. You can see that the three angles in this triangle are 109 degrees, 23 degrees, and 48 degrees. And if you add them, you'll see that they add up to 180 degrees. Also, in a triangle, the sum of the side lengths of any two sides must be greater than the length of the other side. And this is called the triangle inequality. For example, if you have a triangle with side lengths of 3, 4, and 5, you can see that for any two pairs of sides, the number that they add up to is greater than the third. This also means that if someone asks you if they give you three numbers and they ask if they can be the three side lengths of a triangle, you can use the triangle inequality as a quick test to see if that's possible. And the photo on the right, you can see that as the sum of two sides begins to equal the third side, it gets narrower and narrower until it becomes a line, which isn't really a triangle. And if it's actually less than the third side, then you can see that they won't even be able to form the third vertex of a triangle. So here are some two basic questions for you guys to answer. Since they're pretty easy, I think I'll give you guys 5 minutes for both of them. Alright, so I see that some of you have already answered the question, and my TA has also told me that he thinks I gave too much time, so I'm gonna go over the answers now. So, the answer to the first question is that since we know that the sum of the angles in a triangle is always 180 degrees, you can set the third angle as x. So, 35 degrees plus 67 degrees plus x must equal 180 degrees. And so if you subtract 35 and 67 from 180, you get 102 degrees, which is going to be the answer. Wait, I think that's actually not the right answer. I think the TA and I messed up when creating these slides, because if you actually subtract that, you would get 78 degrees, which should be the correct answer. And for the second one, you can just apply the triangle inequality. So with side lengths of 8, 7, and 17, you get that 8 plus 7 equals 15. But 15 is less than 17, so it's impossible. And so if you try making a triangle, here's what it would look like, because the two sides wouldn't be long enough to join together and create a vertex. And you can see on the right that that's another possible way, but like neither of them make a triangle. So now I'm going to explain some symbols that will be used. We're gonna be using these symbols in like slides in the future. So how can we signify that two things are equal in geometry? So for side lengths, we usually use something called tick marks, and they identify sides that have equal lengths. So each side is marked with a certain number of ticks, and if two sides have an equal number of ticks, it means that they're equal in length. So for example, in the polygon to the right, sides BC and CD have equal length, because you can see that they both have two tick marks, and also that sides AB and DE are also equal in length because they both have one tick mark. And yeah, so you can see that that's an example that I just went over. And AE is different from all of them because it doesn't have any tick marks, which means that it isn't equal to any of the other sides. And we use the same thing with angles. So in the little graphic to the right, you can see that for the one on the left, each of the angles have a different number of concentric inside angles, which means that they all have different angle measures. While the one in the middle, you can see that the two angles on the bottom, they each have two concentric angles, or like arcs. So you can see that those two have equal angle measure. While in the triangle on the right, all three angles have the same concentric arcs, which means that all three of them have the same angle measure. And you're gonna learn about what these types of triangles are called later. So now we're gonna move on to classifying triangles. We have two ways to classify them. You can either have it by side lengths or by angles. And there's one exception, which is when the two smaller sides equal the sum of the two smaller sides equals the largest side. And it's kind of not a triangle, and it's more of a line. And you can see on the bottom that that's what it would look like. And since it's not technically a triangle, it's called a degenerate triangle. So how would we classify these triangles by side length? Well, if all three of them have equal length, we call it equilateral. If at least two of them have equal length, it's called isosceles. And since an equilateral has three sides that are equal, it's technically isosceles, because isosceles, it just has to have at least two. So three sides having equal length is also isosceles. And if there are no sides equal, it's called a scalene triangle. So you can see that for the scalene triangle, the side lengths are 2, 4, and 5, none of which are equal. And for the isosceles triangle, that has two sides of length 5 and one of length 9. And finally, for the equilateral, you can see that all of them have a side length of 4. So you can also classify triangles by angle measure. An acute triangle has all of its internal angles less than 90. A right triangle has one of its internal angles equal to 90 degrees. And that's because 90 degrees, as we learned in the last class, is a right angle. So since it has a right angle, we call it a right triangle. And if the triangle has one of its internal angles greater than 90 degrees, it's called obtuse. So you can see examples of each in the bottom. And you may notice that an obtuse triangle, like it might be kind of strange, and it might not be what you usually think about when you think of a triangle. Also, you can think to yourself that it's impossible for a triangle to have two right angles because then it would already have 180 degrees, but since that wouldn't leave any amount left for the third angle. And it's also impossible for a triangle to have two obtuse angles, or like angles that are greater than 90, because, well, if it had two of them, then it would already have if the sum of its internal angles would already be greater than 180, and that's impossible because all triangles, the sum of their internal angles are 180. So here are some questions. I'll give you guys 3 minutes for these. Alright, so it's been 3 minutes, and so I'm gonna go over the answers. So for the first one, you just use the fact that the sum of the angles in the triangle is 180 degrees to find that the final angle will be 90.1 degrees. And since it's greater than 90, it's gonna be an obtuse triangle. And for the second one, well, you use the distance formula that we taught last class. So the side lengths of the triangle are going to be 5, 5, and 6. And since two sides have equal length, it's going to be an isosceles triangle. Alright, so now that we've gone over how to classify them, we're going to make some names for the sides to make them easier to identify. So in an isosceles triangle, the two sides that have equal length are called the legs, while the third side is called the base. And in a right triangle, the two sides that meet at a right angle are called the legs, while the third and longest side is called the hypotenuse. And we're also going to go over some names for these angles. So in an isosceles triangle, the angles that the legs would make with the base are called the base angles, kind of obviously. And the third angle is going to be called the vertex angle, since the third point is going to be called, like, the point that's opposite the base is going to be called the vertex point. And just like how the legs have equal measure, the base angles are going to also have equal measure. And if you look at an equilateral triangle, you'll see that it has all three sides equal. And so basically you notice that for all equilateral triangles, all three angles are also equal. So it's both equilateral and equiangular. Alright, so here's a simple question. I'll give you guys maybe 1 to 2 minutes to do it. Alright, since we're kind of running out of time, I'll only give you guys 30 seconds to do it. Alright, it's been 30 seconds. So you also use the fact that all angles in an equilateral triangle is equal. So you set that angle as x. So you know that x plus x plus x must equal 180 degrees. And so 3x equals 180 degrees. So you divide both sides by 3 to get that x equals 60. And now here's another question. Try to derive an expression for the vertex angle of an isosceles triangle, given that the base angle is x degrees. I'll give you guys maybe 1 to 2 minutes on this one. Alright, I think it's been 2 minutes, so now we're gonna go over the answer. So, once again, you use the fact that the sum of all the angles are 180, and you also use the fact that the base angles have equal measure. So, you can set the vertex angle as b, and we already set the base angle as x. So, 2x plus b is gonna equal 180. So, you subtract 2x from both sides to get that v is equal to 180 minus 2x. And so if you need to figure out what the vertex angle is, you can use this equation easily. And so since we already derived the equation, try to find the vertex angle of an isosceles triangle that has a base angle of 37 degrees. Since we already got the formula, I'll give you guys like 1 minute to do it. Alright, it's been 1 minute, so I'm gonna go over the answer. So once again, you use the equation that we derived before. So you already have that v equals 180 minus 2x. So you just plug in 37 for x, and you get that v is equal to, wait, 100, well, we made another typo, I guess. Since it shouldn't be 72, it should be 74. So the final answer should be 106. And yeah, my TA has apologized. So now we're gonna move on to specialties, like what's special about right triangles. So first of all, in a right triangle, the two other angles are complementary. So to prove this, you know that the sum of the angles in the triangle is 180 degrees. And we're gonna set x and y as the two non-right angles. So we know that x plus y plus 90 equals 180. So if we subtract 90 from both sides, you get that x plus y equals 90, and that means that x and y are complementary. And also, there's a special formula that relates the side lengths of a right triangle, and it's called the Pythagorean Theorem. So here's how to calculate it. So for the two legs, A and B, and the hypotenuse of length C, we know that A squared plus B squared is going to equal C squared. And it's written as the sum of the squares of the two legs equals the square of the hypotenuse. And so I'm going to go over an example of it. So given that the two legs of a right triangle have lengths of 5 and 12, try to find the length of the hypotenuse. So we can set the length of the hypotenuse as c, and we know that the sum of the squares of the legs, so it's going to be 5 squared plus 12 squared is going to equal c squared. And we calculate that as to be 169, and so since we know that 13 squared is 169, the length of the hypotenuse is going to be 13. And now we're going to move on to some more special right triangles. So there's two special right triangles that you're going to need to know for this course. The first is the isosceles right triangle, and it gets that name because two of the sides are equal, and that's what an isosceles triangle is. So as you can see to the right, you can see that the two legs have equal length. And it has two angles of 45 degrees and one angle of 90 degrees. And you can get what the base angles are since you know that they're going to be complementary and they're also going to be equal to each other. So you know that 2x is going to equal 90, so each one is going to be 45 degrees. So here's a quick question. I'll give you guys 1 to 2 minutes for it. So using the Pythagorean theorem, find the expression for the length of the hypotenuse of the isosceles right triangle, given that each leg has length x. Alright, so a lot of people have already gotten the answer, so I'm gonna go over it, and it's also been 2 minutes, I think. So what you do is you use the Pythagorean theorem. So you set the hypotenuse as h, and you know that x squared plus x squared is gonna equal h squared. So 2x squared is equal to h squared. And then we can just take the square root of both sides to find that h is equal to square root 2x. Alright, so now here's the second special right triangle. It's called the 30, 60, 90 triangle because those are its internal angles, you know, like 30, 60, and 90 degrees. And it's special because the side that is opposite the 30-degree angle is exactly half the length of the hypotenuse. And so, I'm gonna give you guys like 1 minute to do this question. So using the Pythagorean theorem, derive an expression for the leg that's opposite the 60-degree angle, given that the length of the hypotenuse is x. Alright, so it's been a minute, so I'm gonna go over the answer now. So once again, you use the Pythagorean theorem. So you know that the leg opposite the 30-degree angle has a length equal to half the hypotenuse. So it has length 1/2 x, since we defined that the length of the hypotenuse is x. So you set the length of the other leg as a, or any other variable that you want. And you know that 1/2 x, the whole thing squared, plus a squared is going to equal x squared. So 1/4 x squared plus a squared equals x squared, and you can subtract 1/4 x from x squared from both sides, and then you square root it to get that a is equal to radical 3 over 2x. Radical is just another way of saying square root. And since it's the middle of class, I'm gonna give you guys uh until maybe 8:40 as a break. Alright, so I think that's been 8 minutes of break, so now we're going to continue and move on. So now we're going to talk about the different centers of a triangle. So, well, you'll need to know 4 different centers, and each of them has some special properties. And all of them are created by the intersection of 3 lines in the triangle. So the first one that we're going to talk about is called the centroid. And it's a triangle created from the intersection of the 3 medians. You might not know what a median is, but it's a line that connects each vertex with the midpoint of the opposite side. So in the figure to the right, you can see that, for example, the vertex A, it connects with the midpoint of segment BC, and same thing with vertex B, it connects with the midpoint of segment AC, and on and on. And you can see that all 3 medians are guaranteed to meet at one point, and that point is going to be called the centroid. And so it's also the center of mass of a triangle. So that means that if you cut out that, like, any specific triangle, and then you can balance it with a pencil by putting it under the centroid. And it also divides the median into 2 parts with a length ratio of 2:1. So for example, in the median from A to the midpoint of segment BC, G divides it into 2 parts. You can see that it divides it into a segment AG, and also the part that's from G to the midpoint of BC. And the ratio of the lengths of those 2 segments is always going to be 2:1. And that's for any median. So here's a practice question. I'll give you guys 1 minute to do it. So if you know that the length of a median of the triangle is 27, what are the lengths of the 2 segments that the centroid is going to split it into? Alright, so it's been 1 minute, I think, so I'm gonna go over the answer. So here's how you do it. So you can use algebra to solve it. So let's let the segments have length x and y. And since the centroid split the median into these 2 segments, it makes sense that the sum of these two segments has to be the length of the original median. So we know that x plus y is going to equal 27. And you also know that the lengths are in a ratio of 2:1. So let's just say that x is going to be equal to 2 times y. And it doesn't really matter the order since we're just asking for the lengths of the 2 segments. So then you just substitute that back into the original one, the original equation, to get that 2y plus y equals 27. So 3y equals 27. You get that y equals 9 by dividing both sides by 3. And after getting that, you can plug y equals 9 back into x plus y equals 27 to get that x is 18. So the two segments are gonna have one is gonna have length 18 and the other is gonna have a length of 9. Okay, so now let's move on to the next center, which is gonna be the circumcenter. The circumcenter is going to be the intersection of the three perpendicular bisectors. So last class, we already went over what the perpendicular bisectors are, and you can see on the right that there's going to be a perpendicular bisector from each of the sides, and they're going to intersect at the circumcenter. And what's special about it is that it's the center of the circle that goes around all three of the triangle's vertices, and that's called the circumcircle. So the center of that is obviously going to be called the circumcenter. So there's some special properties about the circumcenter. You know that if the circumcenter lies inside of the triangle, it's going to be an acute triangle. So the on the top right, you can see that that triangle, the circumcenter lies inside the triangle, so it's going to be an acute triangle. If it lies on the edge of the triangle, it's going to be a right triangle. So you can see in the middle graphic, you can see that the circumcenter is right on the triangle. And you can also see that it's a right triangle. And finally, if the circumcenter lies outside of the triangle, you know that it's going to be an obtuse triangle. And so in the third picture, you can see that the circumcenter is outside of the triangle, and it's obvious that it's also an obtuse triangle. All right, so now we're going to move on to the incenter. The incenter is formed by the intersection of the three angle bisectors, and it's going to be the center of the incircle, and that's the circle that is tangent to the triangle but inside it. So in this graph, or in this picture, you can see that there's three angle bisectors from Q, R, and P, and they intersect at the incenter. And also that's the center of a triangle that's perfectly inside the circle that's perfectly inside the triangle. So if the circle had a radius that was any bigger, it would go outside. And if it had a radius that was any smaller, it would not touch all three sides of the triangle. And the next center is the orthocenter. It's formed by the intersections of the three altitudes. So what an altitude is, it's a line that's perpendicular to one side of the triangle, and it also goes through the opposite vertex. And yeah, so I just said that. And also, altitudes of triangles are going to be used later on to find the area of a triangle. So, yeah. And finally, we're going to go on to what a midsegment is. So a midsegment of a triangle is a line that goes through two midpoints of the triangle sides. So on the picture to the right, you can see an example of one of the midsegments. So there's actually three possible midsegments, since there's three possible pairs of midpoints. So for example, the mid segment that you see here is from the midpoint of AB and also the midpoint of BC. And you can also make another one with the midpoint of AC and the midpoint of AB. And finally, another one with the midpoint of BC and the midpoint of AC. And there are some special properties for a midsegment. So first of all, it's always parallel to one of the sides of the triangle. And more specifically, it's parallel to the side of the triangle that didn't contribute a midpoint to make the midsegment. And also, the length of the midsegment is half the length of the side that it's parallel to. So in this case, DF, the length of DF is going to be half the length of AC. So here's a practice problem. Try to determine the angle that the mid segment makes with the altitude of the side that it is parallel to. So what I mean is, like, for example, the the mid segment of the triangle on the left, and the angle it makes with the altitude on the right. All right, so I think it's been enough time, so I'm gonna go over the answer to this question. So, as you can see, the mid segment and the bottom side of this triangle are parallel. So, and the altitude acts as a transversal between these two parallel lines. And since you know by definition that the altitude is perpendicular with the bottom side, which means the angle between them is 90 degrees, it's also going to be perpendicular with the with the mid segment. So it's also going to form an angle of 90 degrees with the mid segment. And so thanks for attending this class. If you have any questions, you can email us at our emails down here. And I hope you learned something, and I'll see you, well, I won't see you next Thursday because my TA will be covering this class for me on that day.